All right, so this is now the beginning of chapter 3. And in chapter 3, there's really 5 sections, but we're only going to cover about 3.5. All right, we're going to cut out the last one and then half of the second to last one. But the first one is a lot of terminology. In fact, you can see chapter 3 is probability topics. And section 1 is all about terminology, so just getting you comfortable with the probability of things. So there are some definitions here, and I know you can read them, so I'm just going to go over them. But the couple things that I really want to go over is you have an outcome, which is the end of the experiment, and then you also have a sample space. A sample space is basically a list of all the different types of outcomes that are possible. All right, and that's important to be able to identify what is our space, what is possible of happening, and then the event is basically a subset of all the outcomes of an experiment. And then, again, it uses sample space again. And we like to use S as a sample space. You can see we use S, usually denoted S. And it can contain multiple outcomes, no outcomes, all these different things that we can do. And it says standard notations for the events are capital, like event A, event B, event C, and we can keep going, but they're all capital letters. All right, so our S is our space, our sample space, and then we'll say that we have other events. So the probability of this happening, so event A or probability of event B, and they're very common to see A, B, and C a whole lot. Sometimes you can make it make sense to you too. So we can say, what's the probability of getting a 2? Sometimes you'll see the probability of 2 instead of the probability of A, but those are in different circumstances. So more definitions. You also have probability. Probability is a number between 0 and 1. It's a decimal. All right, it's a decimal that cannot be any smaller than 0 and cannot be a number greater than 1. And that's because there's either a 100% chance of it happening or a 0% chance. The probability is the decimal of the percentage. It's the percentage turned into a number, which is the decimal. Okay, and there are 3 different ways that it kind of denotes this, and it says that the probability of an event, so A, is between 0 and 1. It says that if A and B are mutually exclusive events, then you have this, and we'll get to that later. And then also, get back to what we said, the probability of S, remember S is our sample space, so the probability of our sample, our space happening is 100% always. Right, so if our sample space is such and such, what's the probability of them happening? Well, 100%, because either that has to happen or that has to happen. Those are only choices. And then equally likely talks about each outcome has the same probability of it happening in an experiment. All right. Okay, so let's get started with the type of events, and then we're going to move into some problems here. So we have 2 big types of events. The very first 2. There's one called the union, and then the other one's called the intersection. The union, we like to say, you could say the word union, but I get in a habit, and you'll hear me say this. I'll say A or B. Right, so this is how I'll say this, A or B. And you can see I call this the or. Okay, and or means it's in both. It could be the outcome is in A, or it's in B, or it could be in both. It just has to happen. That's all we care about. Okay, this outcome has to happen. The intersection, which I will call the and, I will say it is A and B. And the outcome has to be in both A and B at the same time. All right. And I know that the last section uses a Venn diagram, but I'm going to draw a Venn diagram, and then maybe that'll help you a little bit. So I like to say this, that if I have numbers 1, 2, 3, 4, let's do this, sorry. Let me brainstorm a little differently. 3, 5, and 7. And then let's say my left one, this is my left side. My left side, I have the numbers 1 through 7. Well, there's a 1, 3, 5, 7. So I'm missing 2, 4, and 6. Okay. And then on my right side, let's say that it only consists of even numbers all the way to 10. So I have 2, 4, 6, and I have 8 and 10. So you can see that in this circle here of this Venn diagram that you guys have done since elementary school, maybe secondary school, middle school, high school, somewhere in there. These numbers are 1 through 7. So I have 1, 2, 3, 4, 5, 6, and 7. All these numbers exist on that left side of the Venn diagram. On my right side of the Venn diagram, the numbers that exist are all even numbers between 0 and 10. So 2, 4, 6, 8, and 10. So the union says it can be in one or the other or both. So I look here, here, and here. The intersection is only talking about the intersection where the Venn diagram intersects. This piece right in the middle. Okay, that's where I'm looking at. All right, now the complement is basically saying if A happens, its complement is not happening. So the likelihood of something happening or not is always 100%, right? So I could say, hey, the probability of A, so let's say A is it's going to rain today. Well, the probability of it's going to rain is a percentage. And then I can say the complement is the probability it's not going to rain. So what's the probability of A and the probability of not A? Well, it's 100% because it's either going to happen or it's not going to happen. And so if I say what's the probability of them both, then it's 100%. It's going to happen. Okay? That'll make sense in the next problem. So the last definition is a conditional probability. And it says the likelihood that an event will occur given that an event has already occurred. So we say this is how we say this. The probability of A given B. So another way of saying it is, what's the probability of A happening given that B has already happened? All right, so here's our example 1. You can see there's not, excuse me, there's a lot of blanks, but there's no sample space. So you have to create the sample space. So the sample space S is the whole number starting out 1 and less than 20. So we're going to go and write them all out. So what is S? S is 1, 2, 3, 4, 5. And I'm not going to count anymore because I know you guys can count. All the way to 19. Now it says less than 20, so it's not, does not count 20. So next it says let event A be the even numbers and event B equal to the numbers greater than 13. So if A is the even numbers, 1 through 19, we're going to list those out. So we have 2, 4, 6, 8, 10, 12, 14, 16, and 18. The probability, then B, the sample space of B, numbers greater than 13. Well, we don't count 13, we go bigger, so it's 14, 15, 16, 17, 18, and 19. Now notice how, again, it just has the capital letters. That just means that we're trying to look for that sample space of that event. So what are the outcomes of that event? Letter C says the probability of A. Now we're talking about an actual number, and we're going to use fractions here. So how many events do we have happening in A? Well, let's count them. 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have 9. So we have 9 divided by what is the total number of things that can happen in the sample space? I know you can count because we just counted 1, 2, 3, 4 all the way to 19. So there are 19 numbers here in the sample space. So 9 divided by 19. That's the probability of event A happening. So it's probability of B. We use the same thing, just now the sample space is actually smaller. It's different, but it's smaller. So we have 14, 15, 16, 17, 18, 19. So there are 6 of them. So we have 6 divided by all the sample space, which again is 19. So what it's saying is, what's the probability of event A happening? Then what's the probability of event B happening? Again, remember I told you the probability has to be between 0 and 1. So if I put in these values, these calculator values, or these values into a calculator, and I say 9 divided by 19, I get 0.4736842, etc. What does that mean? Well, that means that number's between 0 and 1. If I do the same thing with 6, I do 6 divided by 19. Number's going to be smaller, but still be bigger than 0. 0.3157 and so forth. So now it asks, what is A and B? It doesn't ask for the probability, just ask for what are the values of A and B. So what's going to happen in both of them? It's kind of like my Venn diagram, that middle part. What's going to happen in both? Well, let's look. What number do they share in common? Well, A has all even numbers and B has numbers 14 through 19. So they share 14, 16, and 18. So these are the values that they share. 14, 16, and 18. So the next one is, what are the possible values between A or B? So remember, A or B means happening in one of them, or the other one, or both. So this includes all of those values. A, that's all in A, that's all in B, but you do not write the repeated values. You don't want to count them twice. So what I mean by that is, well, in A, I have 2, 4, 6, 8, 10, 12. And then 14, 16, and 18 are all counted here. 14, 16, and 18. So I don't write them twice. I just write them once. But I also still have 15, 17, and 19 because it happened in B. So I'm going to write 2, 4, 6, 8, 10, 12, 14. Instead of writing 16, I'm going to write 15, then 16, then 17, 18, and 19. Again, A or B. So happening in one or the other or both. It doesn't matter, but you only count it once. So I would say, what's the probability of A and B? Well, we have 3, right? We have 14, 16, and 18. So we have 3, and then what's our possible? We have still 19 possible. There's still 19 numbers up there in that sample space. So what's the probability of A or B? Let's count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So now we're at 12 over 19. Right, and usually your OR has more values in it because it includes more possibilities, right? You're including all of A and all of B, not just what they share. Then we have, what is our complement of A? Our complement of A is everything that's not inside of A. So if everything inside of A is even, the numbers between 1 and 19 that are even, then what's not inside of A is all the numbers between 1 and 19 that are odd. So those values are 1 and 3, 5, 7, 9, 11, 13, 15, 17, and 19. So now what's the probability of the complement of A? We had how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there's 10 divided by 19. Now the letter G says, what's the probability of A plus the probability of not A? Well, we can do it fraction-wise so you can see it if you'd like to, but I just said in the previous slide, if A is going to happen, it's going to be this percentage, and then the opposite is going to be a totally different percentage, but they're going to always add to 1, and I'm going to prove it to you. So the probability of A is 9 over 19, and the probability of not A is 10 over 19. So if we add them together, so 9 over 19 plus 10 over 19. Denominator is the same, so you add the numerators and you get 9 plus 10, which is 19 over 19, which is 1, which is exactly what I said it would be. So now let's look at the given part, and using the formula that I just gave you, right? It says, what's the probability of A given B happening? So what is the probability of A happening given that B has already happened? In order to do that is we use the intersection of A and B divided by the probability of B. So what is that? What's the probability of A and B happening? Well, we can use all the fraction part of it. That's really what you're doing. So I'm going to show you the better way of doing it. So we're going to say, first off, the probability of A and B happening all over the probability of B happening. Well, the probability of A and B happening is right in front of us, right at the top. It's 3 over 19. So it's 3 over 19. And we're going to say divided by, because that's what really this is, means divided by. The probability of B happening. And the probability of B happening, it's going to be on the right, top right of our screen there, is 6 over 19. So we're going to say 6 over 19. Well, in order to solve this right here, this is a fraction divided by a fraction. In order to do this, I'm going to keep the fraction, change the division to multiplication, and then flip the other fraction. All right, so when you have a fraction divided by a fraction, it's like taking the original fraction and multiplying it by the reciprocal. So 3 over 19 times 19 over 6. And these cross cancel, they reduce, they divide each other out. So I'm left with 3 over 6. And you don't need to reduce it, just leave it as 3 over 6, that's fine. Okay, no reason to reduce. So what's the probability of A given B? It's 3 over 6. So now what's the probability of B given A? Well, are they the same? Well, look, it's different. A given B, B given A. But then when I actually compute them, are they the same? So the way this one reads is the probability of A and B all over the probability of A this time. So we already said the probability of A and B is 3 over 19 divided by the probability of A was 9 over 19. So again, I leave my first fraction, change multiplication, and then I flip my second fraction, which is 19 over 9 now. These 19 divide out, I get 3 over 9. So to answer this question, are the probabilities equal? No. All right, one's 3 over 6, the other one's 3 over 9. Well, that's 1/2, and that's 1/3. They're totally different numbers. So don't just think that A given B is the same as B given A. All right, so let's move to section 2. Section 2 now is talking about independent, dependent, and what mutually exclusive events are. So we're going to go through definitions first. So what we have is first we have, what is an independent event? Independent is that one does not affect the other. Okay, they're two totally separate things happening. Dependent is basically saying that one is more dependent on the other. So if this happens, then this other thing will happen or shouldn't happen. The next thing we say a lot is we say different types of sampling. We say with replacement or without. With replacement means that after we pick it, we put it back in the population, and then it's considered to be independent. Meaning that if I had 3 colored cards, one blue, one yellow, and one red, and I put it in a hat, and then I pull out the card and it's blue. If I use it with replacement, meaning I put the blue card back in the hat, so I still have this red, yellow, and blue card in the hat. What's the chance of me pulling out a yellow? Well, there's 3 in there. Pull it out, 1 over 3. Put the yellow one back in, so now I have blue, yellow, and red still in there. What's the possibility of me drawing a blue? 1 out of 3, every time. They are independent of each other. The first pick does not change your probabilities of the next pick. Now, without replacement means, let's say now I have those same cards in the hat, red, yellow, blue. Let's say, what's the probability of me pulling out red? Well, 1 out of 3, because there's 3 cards in there. But now I'm not going to put the red card back. So what's the probability of me drawing a yellow card now? It's 1 over 2. It's not 1/3 anymore. I only have 2 cards in there. So that's with replacement and without replacement. Last thing is what is mutually exclusive? Mutually exclusive is when they can both happen at the same time, being zero. So, meaning they cannot happen. Okay, so two events are mutually exclusive if the probability that they both happen at the same time is zero, meaning that the two events will not happen at the same time. It's a 0% chance of A and B happening. It's like your Venn diagram. Nothing's in the middle. It's blank. All right, so then example 2. Oh, yeah, example 2 of the chapter. I'm sorry. So draw 2 cards from a standard 52 card deck with replacement. Find the probability of getting at least 1 black card. Well, let's just talk about it. Well, I'm with replacement, right? So let's just talk about 1 card. Forget 2 cards. Let's just say I change this to 1 card. Draw 1 card from a standard 52 card deck. What's the possibility of me getting 1 black card? It's 1 out of 52. Right? That's exactly what it is. What's the probability of me getting 2? Well, if I put the 1 card back in, I have another 52 card deck, but it's not 1 out of 52 because it's a black card. Well, if a deck of cards, if you ever look at a deck of cards, you have 2 different colors. You have red and you have black cards. There's 26 red cards and 26 black cards. So what's the possibility of me drawing 1 black card the first time? Well, there's 26 out of 52. It's 1/2 chance. All right, and then what's the chance of me drawing it again? Well, it's with replacement, so it's the same, 1/2. Okay, I'm going to kind of leave you on that. We're going to keep moving along. So think about when I have a deck of cards and I put it with replacement, then my odds are the same. They don't change. All right, so example 3. Example 3 says, you could read it. It says, let event A equal learning Spanish. Sorry, taking an English class. And let event D taking a speech class. And suppose the probability of C is 0.75 and the probability of D is 0.3. The probability of C given D is 0.75 and the probability of C and D is 0.225. So first off, it says, are C and D independent? So in order for C and D to be independent, there's a couple things you have to check. You can check that that P, the probability of C given D equals the probability of C. So here, let me just write this down. You can say the probability of C given D is the probability of C. Or we can say the other way, so the probability of D given C is equal to probability of D. Or we can say that the probability of C and D is equal to the probability of C times the probability of D. Now, it doesn't matter which one you show. It's just you're showing that they're independent. All right? It doesn't matter which one. So all of these have to apply for them to be independent. So what I'm going to show is I'm just going to show the first one. Mostly because it's given to us really easily. It says the probability of C is 0.75, the probability of C given D is 0.75. Well, they equal, so the answer is yeah. And it's yes. It's yes. And the answer is right there. Because probability of C given D is the probability of C. Now next is, are C and D mutually exclusive? What does that mean? That means that their intersection should equal 0. Well, right here. What's the intersection? Definitely not 0. So that means they can happen at the same time. So are they mutually exclusive? The answer is no. And that's because that the probability of their intersection does not equal to 0. Lastly, it says, what is P, the probability of D given C? And the probability of D given C is the probability of their intersection all over the probability of C. And I know I wrote it as D and C, but that's the same thing as saying C and D. All right? Well, C and D, if we remember, is the 0.225, so it's 0.225. The probability of C is 0.75. You put that into your handy-dandy calculator and you get 0.3. So what's the probability of D happening? So what's the probability of taking a speech class given that you're taking an English class? It's a 30% chance. All right, next example. So it says, in a box, there are 3 red cards and 5 blue cards. The red cards are marked with the numbers 1, 2, and 3, and the blue cards are marked with the numbers 1, 2, 3, 4, and 5. The cards are well shuffled. You reach into the box, you cannot see into it, and you draw 1 card. So here's what you have. R is a red card, B is a blue card, E is an even numbered card is drawn. So what's the sample space? Well, you have red and blue cards, right? And your red cards are 1, 2, 3, and your blue cards are 1, 2, 3, 4, 5. So let's actually, I'm going to color code this just because I can. So my first one is that I have a red card with the number 1. I have another red card with the number 2, and I have another red card with the number 3. Then I have 5 blue cards. I have blue card numbered 1, blue card number 2, a blue card number 3, a blue card number 4, and lastly a blue card numbered 5. So there are 8 possible outcomes in my sample space. So what's the probability? Now remember, probability is not listing anymore. The sample space I've listed. The probability, now I'm talking about fractions here. All right, so what's the probability of me drawing a red card? What do I have 3 of them, right? So I have 3 out of how many? There's 8 possibilities here. What's the probability of me drawing a blue card? Well, there's 5, and there's 8 possibilities. What's the probability of me drawing a red and a blue card? Do you see any red and blue? No, it's either red or blue, so to answer this one, 0. All right, which means something, and we're going to talk about that here shortly. Okay, now what's the probability of E? Remember, E is the even numbered card is drawn, an even numbered. So look at our even numbers. There's a 2, there's a 2, there's a 4, so there's 3 of them. So 3 out of 8. Now the probability of E given B. Again, how do we do that? So here's what it says. It says, what's the probability of me drawing an even number given that they're blue? Well, I can do it the long and dirty way, but how many even numbers that are blue? 1, 2. So I have 2. But wait a minute, is my sample space still 8? It's not over 8 anymore because my sample space now is my blue cards. Well, how many blue cards do I have? I have 5. So it's not 2 over 8, it's now 2 over 5. Again, this 5 is because it says that it's even given that it's blue. So my sample space is now just the blue cards, and there's 5 of these babies. Now let's look at the probability of B given E. What is the probability of me drawing a blue card given that it's even? So first I have to say, my sample space. What is my sample space? It's even. How many evens do I have? 1, 2, 3. We've already talked about. So I'm left with 3. Oh, sorry, wrong one. I have a possibility of 3 that are even. How many are blue and even? 1, 2. So it's a 2/3 possibility. So 66% chance. Now it says, are the events R and B mutually exclusive? The answer to that should be a We go, no. That's proven right there. Their intersection is 0. I said no, and I should have said yes. I'm sorry. Yes, because the intersection is 0. They cannot happen at the same time. Therefore, they are mutually exclusive. All right, chapter 3, section 3, basic rules of probability. This is where we start doing a little bit more mathematics here. So first off, there's a multiplication rule. There's 2 rules. First one is multiplication. And we say this, what's the probability of A and B happening? How do we find that? We can say that's the probability of B times the probability of A given B. And remember, the probability of A given B is right here. A given B is the intersection divided by B, the probability of B. Okay? If A and B are independent, then the probability of A given B is just A. Therefore, if that's the case, then the intersection right here that we've started with, and this is now just A, it's just you're taking the probabilities and multiplying them together. If they're independent. If they're not, then you have to do a little more work. Addition rule. Addition rule is the OR, right? Multiplication is the AND. The addition rule is the OR. What's the probability of A or B happening? Well, it's probability of A plus probability of B minus the intersection. Why is that? Because I don't want to count them twice. If A and B are mutually exclusive, then that means that the intersection is 0. Then I can just add the 2 probabilities together. I don't have to subtract the intersection because there's nothing in between there. What do I mean by that? Let me help you get a little visual here. If I have my Venn diagram, okay? And again, I'm just going to go with some random numbers. 1, 2, 3, 4, 5, 6, 7. Say the probability of A is here and the probability of B is here. If you look at this, and I said, what's the probability of A or B happening? Well, how many do I have here? I have 1, 2, 3, 4 in A, and I have 3, 4, 5, 6, 7 in B. So A or B, I'm saying the probability of all of A, which is 1, 2, 3, 4, so I have 4. The probability of all of B, there's 5 there. And why do I need to subtract it? Because I have counted this twice. So I've counted 3 and 4 twice. How is that possible? I can't count something twice. I counted it in A and I counted it in B. So I can't count it twice, so I have to subtract the intersection out so I don't include them. But let's say that this didn't even exist. There was nothing in here. So if they're mutually exclusive, then there's nothing for me to subtract. There's nothing that I counted twice. I counted 1, 2, 5, 6, and 7. Nothing in between. All right, example 5. Example 5 says a community swim team has 150 members. 75 of the members are advanced swimmers. 47 of the members are intermediate swimmers. The remainder are novice swimmers. 40 of the advanced swimmers practice 4 times a week. 30 of the intermediate swimmers practice 4 times a week. And 10 of the novice swimmers practice 4 times a week. Suppose one member of the swim team is chosen randomly. Well, first off, how many do we have? We have 150. So we know that the probability, unless it says given this, it's going to be 150 in our denominator. So let's look at the first one. It says, what is the probability that a member is a novice swimmer? Right there. It doesn't say given anything, so I know I'm 150. Something divided by 150. Well, how many novice swimmers do I have? Well, look, if 75 are advanced swimmers, 47 are intermediate, the remainder are novice. Well, 75 and 47, add them together, subtract my 150, that gives you 28. So it's 28 divided by 150 is your answer for A. The probability that the member is a novice swimmer is 28 divided by 150. Now, what is the probability that the member practices 4 times a week? Well, it says 40 of the advanced swimmers practice 4 times a week. 30 the intermediate swimmers practice 4 times a week, and 10 of the novice swimmers practice 4 times a week. Does it say that it has to be given that they were something else? No, it doesn't. So I know my denominator is 150 because I'm still choosing all of them, but I'm going to now add the 30, the 40, and the 10 together. And that gives me 80. So it's 80 divided by 150. All right, next. What is the probability that the member is an advanced swimmer and practices 4 times a week? It doesn't say given that they practice 4 times a week. It just says that and. So I'm still out of 150. Now I look at my probability. They have to be an advanced swimmer and practice 4 times a week. So you go back to our statement up here. And right here it says that 40 of the advanced swimmers practice 4 times a week. So I put 40 here. I want the advanced swimmer and practice 4 times a week. So next, it says, what is the probability that a member is an advanced swimmer and an intermediate swimmer? Are being an advanced swimmer and intermediate swimmer mutually exclusive? Why or why not? Well, can you be advanced and intermediate? No, you're either one or the other. Pick a side. So these are mutually exclusive. So what is the probability? The probability of advanced, of advanced and intermediate is 0. They can't be both. Are being an advanced swimmer intermediate mutually exclusive? Yeah, because you can't be both at the same time. Either one or the other. All right, so E, it says, are being a novice swimmer and practicing 4 times a week independent events? Why or why not? Well, I mean, you need to prove it. You need to prove so. Novice and practice 4 times a week. So I'm going to prove this. I'm going to say that the probability of them being novice, and practice 4 times a week I shouldn't write the number 4 there. I should write the letters here. Which we did. Let me see, what did we do? We did novice. Did we do novice swimmer? No, we did advanced swimmer. So a novice swimmer that practices 4 times a week, there's 10. So novice and practice 4 times a week, there's 10. So it's 10 out of 150. All right, well, I have to prove that they are, if they're independent, then the intersection is equivalent to them being multiplied together. So I need to prove that that is the same as the probability of being novice times the probability of practices 4 times per week. So the probability of them being novice, as we already said, was 28 out of 150. And now I have to say the probability of them practicing 4 times per week. It doesn't say who, it just says practicing 4 times per week. So how do I find that? I go up here and I say, well, 40. Where is that? Sorry, 40, 30, and 10. So what I do now is I say that I have this 30, 10, and 40, but we already did that. It's 80 right here, 80 over 150, because there are 80 members that practice 4 times per week. Just 80 over 150. And when I get the fraction, sorry, I have these fractions, but I need to know the decimal of these. So 10 divided by 150, if I put it into my calculator, 0.066 repeating. And then if I put the 28 over 150 times 80 over 150 in the calculator, I get 0.0996. It's 0.995 repeating, so we're going to round 6. You see, these do not equal each other. They don't equal. So are they independent? No, they're not independent events, because if they were, those two things would equal each other. All right, chapter 3, section 4, we're just going to cover the contingency table. So remember I told you we cover 3.5 sections. So contingency table is displaying all of the data in a table with rows and columns. And you're going to see that all the rows add and the columns add, and I'll show you how all that works. So first off, before I get to the example, I want to show you something. All right, before we start solving it, so let's pretend like this is not here right now. Let's just look at the table here. It says, suppose a study of speeding violations and drivers who use cell phones produce the following fictional data. So drivers use cell phones when driving. Here's a 25, 280, and 305. You can see that if you take 25 plus 280, that equals to 305. Right? Same thing here. If I take 45 and I add it to 405, sorry, 45 plus 405, that gives me 450. Likewise, if I had to go straight down here, 25 plus 45 is 70, and 280 plus 405 is 685. Okay, another way of looking at this is 70 plus 685 is 755. And then 305 plus 450 is also 755. So 755 tells me the total that I've had of all the data that I have. How many pieces of data I have? I have 755 pieces of data. All I've done is just put them in categories now. Okay, now I can read this table. This says a speeding violation last year. So how many had a speeding violation last year? Add them straight down, 70 total. How many had no speeding violations in the last year? Add them straight down, 685. Now I keep going this way. How many use cell phone while driving? 305 use a cell phone while driving. How many do not use a cell phone while driving? 450 do not use a cell phone while driving. Okay, so you can see you can add straight across or down depending if you're looking at the row or the column. So now let's see if this makes it a little bit easier to read these. So A, it says, find the probability of a driver is a cell phone user. So what is the probability that someone is a cell phone user? Well, first you say that, okay, well, the number of cell phone users is right here. Use a cell phone while driving, 305. So this is 305. That's just a number. Probability is talking about a fraction. How many people do I have total? 755. That is the probability of a driver is a cell phone user. Okay, next it says, find the probability a driver had no violations in the last year. Oh, I don't want to do that, sorry. So probably they had no violations last year. No speeding violations last year, right here, 685. Again, my total, 755. All right, next it says, find the probability that a driver had no violations in last year and was a cell phone user. You don't have to do a lot of multiplying or adding. You just look at the table. So they have to be a driver that had no violation last year. So we're looking at this column right here. And has to be a cell phone user. Looking at that row. So where do they intersect? Right here. Here's the intersection. 280. So So this one is 280 divided by, again, 755. It doesn't say given they were anything, just says of these people. So it's 280 divided by 755. So next it says, find the probability that a driver is a cell phone user or the driver had no violations in the last year. All right, we can do that. So first, driver is a cell phone user. Right here, we already established this. 305 over 755. Or it means we're going to add. The driver had no violation last year. So this driver had no violation right here. And what I want to show you is, look, I've used this column and I've used this row. What did I use twice? I used the 280 twice, which means that first I'm getting ahead of myself. This should be 685 over 755. But I've used the 280 twice. I'll do minus 280 over 755. And then I can add all that together. And that's going to give me 710 over 755. If I don't subtract the 280, I end up with a number larger than my total. And that's not possible. Does that always happen adding over? No. Sometimes that's not a good flag to look at. But in this case, it did happen. All right, letter E, it says find the probability of a driver is a cell phone user given the driver had a violation in the last year. So now I'm looking at reducing my population size. So first off, the driver is a cell phone user. Let me erase this here. So I know the driver is a cell phone user. So I'm in this first row here. Okay, but it says given. Now when it says given, I'm only looking at one specific thing. It says given the driver had a violation last year, so I can only look at this column. And if I'm looking at this row, I shouldn't even go all the way across. I should only look at this one or this one. So the 25 is what intersects it. So here it is 25, but instead of being 755, it's the total of my given, which is 70. So it's 25 over 70. Our sample space is reduced to the people who only had a violation. That's what it says, given they had a violation last year. All right, so next it says, find the probability that a driver had no violation last year, given the driver was not a cell phone user. So you could do it how you want, but it says that they do not use a cell phone. That's the given. So I'm looking at this row here. Which means my total is this thing right here, the 450. That's the only number I care about. So 450. So first off, is the driver that had no violation. I'm looking at this column, which is this number right there. So 405 over 450. This would be my answer here. Okay. All right, that ends our chapter 3 lecture.